Hello everyone. So myself Sanskar Soni and I was working on the project Passive Sonar Simulation. So Passive Sonar Simulation is a broad term. So my project was of effective detection of range of a passive sonar at a particular location, say depth, latitude and longitude. So it's like it uses a several variables, and basically what the project is depends on effectiveness and the accuracy of the calculations and the values I got at a particular location of certain variables. So as we proceed, I will demonstrate how we do that. So this is an passive sonar. So passive sonar is basically a ear of oceans. So as we have ears, we listen. So as a passive sonar listens everything in the oceans. So we have to predict that how far an passive sonar can listen at a certain detection probability in a particular SNR value. So we uses this passive sonar equation as our logical basis. So the three key variables used here are source level, transmission loss and the noise level. SNR is a variable which we use to calculate the detection probability at which we can have the maximum range of a passive sonar. So we discuss these all in detail in further slides. So as we go through SNR is basically the ratio of the desired signal and the noise across the noise across the instrument. So it gives like it is a we can calculate ROC curve we have graph between detection probabilities and the false alarm probabilities at a given SNR, and the false alarm probabilities are ranging between it's range between like minimum to the maximum at certain points, like 10 to the power minus 10 to the it goes to 101 and as further. So we get the detection probabilities with certain formula. As we go through the source level is basically the signal estimated by vessels and the ships present in our area, in our desired area in which we are working on. So source level basically is calculated by Wittgenstein model, and the input data of Wittgenstein model is basically the is basically like AIS data, which have the what we say is which have the data of every ship, and we can calculate the source level from every ship. So as in our project, we take the average of all the ships present in our desired area. So we go through the transmission loss then. So transmission loss is a key thing which we are working upon, because this is a main key factor which we are working on and which we are tracing, and from that we are getting the maximum range we want. So transmission loss is just not basically the loss of signal from the original signal. It is the loss, but it's not linearly dependent on range in the ocean. It depends on the seafloor acoustic parameters and the sound speed profile, temperature, salinity of a particular location, and various levels at oceans and various challenges in oceans, and all of these considered, we can calculate the transmission loss. And going ahead, we calculate the transmission loss using the Pyram model. This is the universally used model now for the calculation of the transmission loss versus range. So Pyram model basically depends on the RAM algorithm, which is algorithm is based on the parabolic equation algorithms, and there's a certain new methods also like DBN, which uses artificial intelligence, and this uses all four existing four methods, the data we collect from them, and we put it in the model and train the model by this thing. So this is currently maintained by Marcus KD, and it is an open library on Python. So as we go through, where we encountered the noise level is basically the ambient noise matching at a ambient noise mapping at a certain place, as I shown the graph. This is the 2D ambient noise mapping at a certain depth, and we predict the noise level at a certain location. We use the NumPy libraries to predict the data, and this basically noise level is the ambient noise level, and the shipping noise, mammals noise, and so on. So basically we use the shipping noises in our project. We can further develop it using 3D ambient noise mapping, and this gonna be very nice ahead. And again, this is basically the correction factor in the sonar equation. When we go through the sonar equation, the R again we see it basically is basically the correction factor which actually determines what extra because of the instrument, what extra noises we collected, and so that's the basically the array gain. And in name suggests that array gain, the extra was collected by arrays at the sonar. Detection threshold is basically the we calculate using false alarm probability. The detection probability we got from the SNR value which is given to us. So these are two equations given, which is RT, which is logarithmic of false alarm probability divided by logarithmic of detection probability subtracted by 1, and we put in detection threshold formula. So as we got detection threshold from this equation. As we proceed the Gaussian process regression, this is the machine learning model we are using to predict the data of transmission loss, transmission loss versus range thing, which we got from the PyRAM model. So Gaussian process regression is basically the Bayesian approach. So what Bayesian approach tells us is it tells us that we have certain data and we have to predict the thing. It's basically what the Bayesian approach is. So Gaussian process is like infinite dimensional multivariate Gaussian distribution. As the data we got from PyRAM, it follows actually the Gaussian distribution, Gaussian random distribution, and so we are using the Gaussian process regression. Gaussian process regression basically is the multivariate Gaussian distribution. It works on multivariate Gaussian distribution. So Gaussian distribution is basically the normal distribution we see in the one dimension. The multivariate Gaussian distribution explore in multiple dimensions actually. So when the Gaussian process regression, we have a function of which has a parameters of mean and covariance. So these are the two stats we are using in Gaussian process regression. So I will show the show some graphs and the show some graphs and stats according of Gaussian process regression. These are the two graphs I showed here. One Gaussian progress regression with 0 training points, and one Gaussian progress regression after 3 training points. So Gaussian progress regression with 0 training points is a single line with basically it doesn't predict anything. It's a single line. So when we put some training data set, there are three training data sets you see which collapses. So there's a three points. So actually 4 points collapse. So we can see, and the curved part, the extra part here is uncertainty in prediction, which basically the standard deviation from the mean value. These are the predicted mean values which we can show with the red line, and these are the uncertainty in the predictions what we get from Gaussian process regression. This is how actually it works. So it is a large sample data set, and this is how Gaussian process regression fit on that data. Basically why we use Gaussian progress regression is the question. So the answer behind is that what the data we have, it follows the Gaussian distribution, and also the Gaussian process regression works on small data sets very well. It's of time complexity of n cube, which actually makes it for the small data sets. So at last, the engine we are using the MATLAB engine API. In the there is a function which is ROCSNR inside this. It actually has a certain library. MATLAB has a certain library says phased array. So that gives a lot of opportunities and functions to us to apply on the passive sonar and the sonar basically on the world. because I can use the simple equation, but I use this as a further possibilities in the project, so we can go at a faster rate, and it can it can give a whole lot of amount of technologies and advancements in the sector. So for using the project I created, one must have the MATLAB installed in their PCs, and also the phased array library. When this is an ROC curve which we get from the ROC SNR function from the MATLAB Engine API, which gives us the detection probabilities and the false alarm probabilities in particular SNR. And this is the final equation we are using to calculate the figure of merit, and we then trace the figure of merit on transmission losses range data we get from PyRM using the Gaussian process regression I described earlier. So all these variables are used in this source level, noise level, which we talked about, error gain. Bandwidth is a property of the instrument of the sonar, and the last is detection threshold, which we talked about. As and the and I used the GUI. I used the Teak Inter, the Python library, which is the GUI library, GUI developing library. So it's a good working with Tkinter, and these are some interfaces from the project. So this is in login sign up window, and we can register and login from the same. And this is the actual window what we are main window of ours. Taking inputs of SNR, the location which comprises of depth, latitude, longitude, bandwidth, and again the properties of the instrument, and it gives us range in the nautical miles. So at last, thanks MRC and Arnav sir. You are the guide for us throughout the internship. You talked about research, and we know, and now we know how to do detailed research, and just not predicting the things. And Shidhar sir was the base of our internship. He is available every time, every time we feel some obstruction. Every meeting is incomplete without Shidhar sir, and it was nice working experience with the Shidhar sir, and he's really cool. I must say.